there's no doubt, I don't think, in any of your minds that when I release the meter stick, it's going to swing downwards, right? I want you to be able to express why that's true in more than just information about like energy. For example, if this is the pivot point, it should be clear to you that there is a force acting on the meter stick. And that force is going to cause a torque. And because there's a torque on the meter stick, it's going to experience an angular acceleration, which is going to cause it to move and rotate downwards. It's pivoting about this point. And because it's pivoting about this point, it doesn't actually change its location. It changes its orientation, its direction, because it's locked in here. The force applied here makes this net force on the meter stick unbalanced. That's important too, because it's going to come up again when we talk about momentum here in a couple of weeks. So there's a lot of things happening at this pivot point. And I'm not sure I could tell you where or what direction the force is acting at the pivot point. I mean, right now, I'm sure the force is straight up, but I'm not sure if it stays like that. Because as this thing rotates this way, I can imagine that direction of that force, in order to keep the meter stick here, might also change direction. Can you imagine that too? So I think this is a complicated system when it comes to forces. I don't believe it's particularly complicated when it comes to energy. I know that the center of mass has been lifted from where its lowest point could be. Now, before we go into it, you do understand we can manipulate that. Right? I could have drilled the hole here. That manipulates the problem a bit. Does it change it? Does it really change it in a way that makes the what you're going to have to do very different? I mean, it's just the moment of inertia. It changes the torque, but it really doesn't change what's going to happen. On the other hand, if I mount it at its center, nothing would happen. Right? It's mounted at the center of mass, so it's not likely to do anything at all. So there is something to be said that this distance where I drilled the hole makes a difference in the result. And there's been problems where they've made that the variable. And had you come up with, well, what do you get for the energy, or what do you get for the velocity as you change this location? Don't always think that the variable has to be the same every time. How fast is it going when it reaches the bottom? They don't. They mix it up. Now, to understand what I'm going to ask of you, you have to understand that the meter stick is going to rotate until it's in a position like this. Meaning it will rotate to this position. And it's going to do so because there is an unbalanced torque acting on the system. What I would like you to tell me is how fast is the end of the meter stick moving? That's what I would like you guys to tell me. Now, to understand this, this is a conservation of energy system. I have lifted the center of mass until it is aligned with the pivot point, and then released it, and the system is going to swing downwards. So I'm going to give you guys a minute because I think you need to try and do this on your own, but I hope that you will be able to deal with the fact that I have gravitational potential energy when I pull the meter stick to the side, and it's going to be converted to kinetic energy when it is perfectly vertical. You will probably need a moment of inertia of the meter stick about an end, although we talked a lot about it yesterday. I'm willing to give it to you today. But remember, I want the linear velocity of the end of the meter stick. So why don't you guys take a few minutes, kind of bang away at it, and all right, so I don't want this to take up a lot of time because we have other things that I think are more valuable. This is our introduction here to dealing with conservation of energy on a rotational scale. Although there is, several forces acting in the system, there's no external force that acts in this system to take energy out of the system. Meaning the gravitational force is a conservative force. It can convert the gravitational energy into kinetic energy. The force that's here is an external force, but it doesn't cause an external torque because it acts at the pivot point. You might not have thought of this, but I'm going to need you to start thinking like this. So the force that acts at the pivot point is an external force. It would take away momentum. It would do things like that, but it's not providing an external torque to the system, so it doesn't take any energy out of the system. That's an incredibly important implication. And so I need you to make sure that you're getting that in your notes, that we need to take a moment to kind of consider what are the parts of the problem that are contributing to the unbalanced force and which ones are taking away energy. And I'm kind of building in time because Skylar's getting herself relogged in. So although she might have the prevailing Wi-Fi, even she was unstable and needed to pop in on her phone or off her computer. Or something like
taking all my Wi-Fi.
Well, I like the heavy bandwidth options here. So what this means for us is that we have gravitational potential energy at the start of this problem. And if we assume that when it's down here, it's at its lowest point, then all of that energy has been converted into, in this case, rotational kinetic energy. So the first thing to do is recognize this is going to be mgh, but I think with h, we can replace it with something that makes more sense, but it's not L. And a lot of people think it's going to be the entire length of the meter stick, but it's not. H represents how much the center of mass was lifted. The work in lifting this is the work required to lift the center of mass, which is L over 2. That's a pretty common mistake, but let's not make it. In addition to this, we're going to have 1/2 I omega squared, but I want the velocity, the linear velocity of the bottom of the meter stick. So instead of putting omega in there, I'm going to make a substitution and recognize that I want the linear velocity at the bottom of the meter stick. And at the same time that I would have put omega in there, I'm going to put V over L in there to indicate I'm looking at the bottom of the meter stick. Now, before I work through my answer, I do want you to consider a couple of things. First, the entire meter stick will have a single omega when it's at the bottom, a single final velocity when it makes it to the lowest point. But every single part of the meter stick is going to have a different linear velocity. So I expect L to be in my answer, to tell me where this velocity is, something about the length. I expect that the mass will probably cancel out, don't you? Doesn't mass almost always cancel out for a thing like this? But I do think the shape is probably going to play a role in the answer. Something about its moment of inertia is probably going to exist in the answer somewhere. So mgl over 2 is on the left side, 1/2 times moment of inertia, 1/3 ml squared, times v squared over L squared. So hopefully you guys who are working this out, and I didn't come by and check your work, mostly I just didn't want to. We start to realize there are things here we can start to cancel. When I'm done, I get a very simplistic answer, 3GL. I think the 3 is a remnant of the moment of inertia. Something with a different moment of inertia would probably have a different number there. The G, of course, makes perfect sense. I would expect my velocity to be dependent on the acceleration. The L makes perfect sense. I would expect that my remnant of my velocity would have something to do with where I am on the meter stick. All of those things tend to make sense to me to be in this answer. But it's at this point where sometimes the problem gets turned on its head. Like there's a spider hanging on the bottom of the meter stick. And yeah, they gave a problem just like this a couple years ago. It wasn't a spider, it was a bee or a hornet or something. What would be the force the spider would have to apply to the meter stick to stay on it at the bottom? I'm saying that knowing I'm transitioning to a completely separate problem. And I don't know if you know it or not. But at the very bottom, the spider's in circular motion. And because the spider's in circular motion, there must be an unbalanced force acting on the spider in order for it to stay in circular motion. Yes, that slapping of the forehead that I saw William do. Yes. At the very bottom, the spider's experiencing probably two forces. It's got its own weight, mg for the spider. But I think the spider's, he's holding on. Now, I don't know what this force is. And a lot of people argued with me about this force in sixth period. I don't know what the Spidey force is. His little clingy legs are doing something. I don't know. I don't tend to smash spiders, but at the same time, I don't observe how they hang on to crap. So I'm just going to say he's got some hanging on-y force, a tension or something. I don't know what it is. I don't care what it is. I just want to solve for how big it has to be. Now, this part shouldn't be too terrible for you guys to work out. We've done this dozens of times before. I would expect that the answer has something to do with how fast he's going. I would expect that the answer has something to do with how much mass he has, because we're looking for a force. I would remind you, though, that for him to hang on, the net force has got to be equal to MAC. So I do think this will be dependent on where on the meter stick he is. I would probably use mv squared over r because we have v. But I wouldn't leave out the fact that there are two forces, tension minus mg equal to mv squared over r. Now, this part's not terrible. It's not hard. You should look at it. You should work it out because you're going to be surprised, I think, by the result. Well, you might not be. I was the first time I did it. We done yet? I am. L's cancel, which means that no matter, where on that meter stick, you're gonna have to hold on with a lot. I thought that was pretty crazy, though. Are you guys still catching up to me? You shouldn't be. You should be done. Square the 3GL, you get 3GL, divide by L, L's gone. So 3mg plus mg gives you 4mg. This is why America's Funniest Home Videos exists, right? Because I don't think any of you can hold on with like 4 times your weight hanging off of you. I want to imagine you and 3 of your closest friends holding on to your shoulders and you're just holding on. That is, I mean, some of you, I know, I see you guys going to the gym, no, not really. Some of you, maybe, but still, could you hold on with 3 of your buddies hanging on your back? I just don't know. I mean, that's a lot. It's a lot to ask, which is why when people think they can do stuff and you watch it, on like Reddit, you find out that they can't. That's why I love What Could Possibly Go Wrong. That subreddit, good stuff. Hold my beer on Reddit. That you want to see some funny stuff. That's a good place to look. Hold My Juice Box is my favorite because it's little kids doing this kind of idiot stuff and finding out the hard way that physics hurts. So Hold My Juice Box, good one to take a look at. All right, so what do you think? Straightforward example, I believe, that brings together conservation of energy, the connection between linear and rotational velocity, and of course, net force. You see all the pieces there? The only thing that's missing, there's a ball at the bottom and there's a collision so that we have conservation of momentum. And then you would have a full FRQ. This is what the problems are like. But I'm hoping you see there's a certain amount of proceduralism to these problems. And I mean, how many different ways can they arrange these problems? Not nearly as many as you think. Just like talking about E&M, once you've seen a few of these, they're really similar. They can mess with them. I could put the pivot point here. That does change the problem. Does it change it very much? No, it really doesn't. It changes the moment of inertia, and it changes how much energy we had to start with because we're not lifting it as high anymore. But that's all it changes. Those are little things. So if I do that, it's to see if you understand that I have a change in how high it was lifted and whether you can use the parallel axis theorem. That's the exact reason why they would change that for that purpose only. So they don't change things just to see if they can make trip you up. They want to know, do you remember to use the parallel axis theorem when it's not at the end or the middle? Do you remember you have to readjust for how much is actually being lifted? Do you remember the idea of center of mass? That's all they're trying to do. I really would prefer to let you guys run with this and not spend time on class on it. But 6th period and 7th period made it very clear that we can't do that. So I want to come back to the inclined plane problem for a little bit. And we've talked about these in a colloquial fashion. Let the ring and the disc run down the desk. We do need to recognize that in here, there's going to be a certain amount of calculation required. So I've got a incline angle theta, put a disc on it, the very top, and yes, it is specifically a disc. So 1/2 mr squared is its moment of inertia. I'm going to say that there's enough friction so that this point stays in contact and it doesn't slide down the ramp. That's important. The fact that it rolls down the ramp and doesn't slide down the ramp specifically indicates that it's going to be going slower when it makes it to the bottom, because my energy now has to be split. When it gets to the bottom, the object's going to have two velocities. The center is going to be moving with some linear velocity v. But it's also going to be rolling with some angular velocity omega. One of the important details here that I think you guys need to kind of make sure you understand is if it's rolling, we get to bring to bear a connection between its linear velocity and its angular velocity. And that connection is the radius. Now, what this ultimately means in the long run, in the far off details, is that there's two kinds. There's two kinds of kinetic energy at the bottom. So although we start with gravitational potential here at the top, when we get to the bottom, we have to divide that total amount of energy into two buckets, not just one bucket. If it was sliding with no friction, it would all just be translational kinetic energy. And if we were doing that, you guys should have in your mind how fast it would be going if it slid without friction, right? It's the same speed as if you just dropped something. That should be in your head as a means of comparison, because we should recognize that when it rolls down, it's probably going to be going slower than that. So I want you to see if you can't figure out what this answer is. Can you employ what we just did on a little bit more complex scale and figure out how fast the object is rolling at the bottom of the hill? So again, I'm gonna give you a few minutes to do so. We have, 10 minutes, I think. More than 10, a little bit more. I'm gonna stop recording.
Cancel out.
Elise, man, your cat, like she's huge.
She is not. She weighs 4 pounds.
She was close to the camera then.
Yeah, she's 19 and weighs 4 pounds.
19.
Yeah.
That's an old girl. We got a brand new cat in my house. I've had it for like 2 years. I hate that cat. It was my idea to get the cat, and I hate that cat. Hate strong. I want an ugly cat, and I got an ugly cat. But then my daughter, the cat just adopted my daughter, my middle kid. And I've been mad at them both ever since. It's supposed to be my cat. I wanted a cat. All right, so how much energy do we have to start with? Just MGH. This one starts off pretty easy. But then we have 2 forms of kinetic energy. So 1/2 mv squared, sure. But now 1/2 I omega squared. Now the thing about these problems is that we don't want to leave it like this. We're trying to figure out how fast it's going at the bottom. So either we get the rotational speed or the linear speed. Which one do you think is most reasonable to get? I think the linear too. It's easier to measure the linear speed. You can just watch it, time it, or something like that. So the very first thing, and this is a huge expectation for the exam, is that you're going to make this substitution. Almost every time one of these rolling questions is on the exam, there's a point just for doing that. So don't lose that point. This requires that you have one basic knowledge or understanding, and that is you have to be told it's rolling. I'm saying that because if they don't tell you it's rolling, you don't necessarily know. It could be spinning and sliding, but not rolling. The word rolling, though, means that is true, that you can use this relationship. I've said that like 6 times, but I don't know if I've said it like 6 times in this class alone. So let me make sure I emphasize that. This object can be sliding down the ramp and spinning some, but not be rolling. They've asked the question in the past where it started sliding and asked how far did it have to slide until it was rolling. So be aware, we are just looking at the beginning of this, the assumption that it is rolling from the start. But we have to be prepared to do the full problem, to figure out what's going to happen when it's not rolling. So when we establish that it is rolling, we can start making, and I'm going to make both substitutions at once. You have to make the moment of inertia substitution for sure, but you also need that V over R substitution at the same time. Notice this is not accidental. The R's cancel out. Anything that rolls, you're going to see these R's cancel out almost every time. You're also going to see the mass go away. That's not an accident either. Just like before, the mass, I expect it to go. Now, this is because we have the moment of inertia. We have a value to use here. If we didn't, then your moment of inertia appears in the end of the problem. But having a moment of inertia means that we get to cancel some stuff out. Look, I'm a little freaked out about this in general. Freaked out is really an overstatement. I am not freaked out at all. But I want you to recognize, I think it's weird that the radius has nothing to do with this. That if you had a huge beach ball or a tiny little ball, they would both roll down to the bottom at the same speed. As long as they have the same moment of inertia, a disc like a record, I don't know, you have no idea what a record is. So a disc like a solid pizza or a little tiny coin would both roll down the desk the same. The fact that one has a bigger radius than the other doesn't change that at all. And I think that that is an interesting circumstance, something to keep in the back of your mind, tucked away, that even if it's really big, it's the shape that determines how fast it's going, not anything else, not its size. Right? The R disappeared. All that is left here is that 4/3. And that 4/3 is a remnant of the moment of inertia. We would have got 2 if it wasn't there. But because it's there, we get this remnant. Interestingly enough, if you had had a ring and not a disc, this wouldn't have been 1/4, it would have been 1/2, which would have created an even slower velocity. So
Wait, Mr.
Go ahead.
Sheldon,
yeah.
would it be 3/4 instead of 4/3? Yo, you gotta. Never mind.
No. Oh, I wanted to do it. I've got my mics changed so they can hear better what you guys are saying in the room. But so Xander, you figured out your math mistake?
Yeah, I just had to say it.
Good. It made us all very happy to hear it. Yes, sir.
What is that radical 2G8? What is that you put there?
If you had just dropped something, it would reach the ground at 2GH.
Okay, because
And
threw me off. I thought that you gave us the velocity.
no. This is what would happen also if there was no friction at all.
Dang it.
So
I would've
folks-
found the right answer if I didn't. I plugged
Sorry.
in that for like.
Oh,
speed.
no. I left it there to make sure that we had something to compare at the end. It's going slower than it would have if it just slid down. And folks, please, I'm going to run out of time, but I need you to hear this. If there was no friction, the system wouldn't have rolled. If there was no friction, this term would have been gone. Block or disc, they would be treated the same because they would have just slid to the bottom, and this would have been the speed. It is rolling that specifically transforms the energy into two types and therefore slows it down, but it doesn't have less energy. It's just traveling slower. Now, this is not really what I want to talk about. If you'd had AP1, of course, you know about this, but more importantly, most of you can get acclimated to this part pretty quick. This is just a redress of what we did first semester. We're just adding a form of energy here to compensate for the fact that the object has two kinds of kinetic energies. What I need you to recognize is that you could be asked to figure out how much friction there is up there. That problem isn't as obvious as it seems. And part of the reason is you can't use what we know about friction. We don't know that we're at the threshold for static friction. We're probably not. Rolling friction is usually really small, which means you're never going to be using this unless you know you're at the absolute threshold when something's about to break static friction. But it is static friction that causes things to roll. So if I wanted to figure out the frictional force, that problem is actually kind of tough. The friction acts this way on the object, towards the top of the ramp. That's what gets it to roll. But there's still mg sine theta down the ramp. Now, we could evaluate this from the standpoint of forces, or if you really want to see this quickly, you could find the acceleration real quick. You know the final velocity. You know the initial velocity was 0. You might not know the distance that it traveled, but I'm willing to tell you that the distance it traveled is h divided by sine theta. Take just a quick minute, use a motion equation, and figure out the acceleration. I gave you x, initial velocity, and final velocity. You will not be surprised by the answer, but find it real quick, please. Hurry, hurry, hurry. We do not have much time. In fact, we have no time. So before that bell rings, look, I want you to find the acceleration. And I want you to do it because net force equals ma. Along the ramp, there are two forces, mg sine theta and friction. Tomorrow, I want you to come in with the size of the frictional force. Okay? Please do that. Spend a few minutes and do that. It will not take you but a few moments to get the acceleration and then to plug it in here. Because all you got to do is plug it into F equals ma, and we're going to get it. You'll get a value for that frictional force. We need it for tomorrow. All right. That's it, folks. So